No, I'm kidding.
All right, and number one, the first thing I want you to do is explain why the mean value theorem applies to the function over the interval from -2 to 0. So yesterday we talked about the mean value theorem. What are the conditions that have to be met for the mean value theorem to apply? Maggie?
Calculus slope has to equal the...
Well, that's what happens if the conditions are met, right? Hold that thought. In like 5 minutes, I'm coming back to you. Has to be continuous and differentiable. So let's start with continuity, okay? Tell me about your function.
Well,
What kind? Yeah, there we go. Let's start there. It's a piecewise function. So each piece of the piecewise function, is it continuous on its own? Yes. So where's the only place where we're going to have to ensure continuity? -1. So how do we determine if they are or are not continuous at -1?
plug in -1 to both.
Good. So we want to know that 11 times -1 plus -1 squared equals -1 cubed minus 3 times -1 squared minus 6. Yeah? What do you get over here? -10. What do you get over here? Are we continuous? Yes. Okay. What did you do, Martin? What else? What else has to happen in order for the mean value theorem to apply?
It has to be different.
So in order to determine if it's differentiable, we probably want to know what the derivative is. So if the function is a piecewise function, its derivative is a piecewise function. Okay? So what's the derivative of the top piece? Which is true for x less than -1. And what's the derivative of the bottom? 3x squared minus 6x for x greater than or equal to -1. So 11 plus 2x, is that defined everywhere? 3x squared minus 6x, is that defined everywhere? So where might this piecewise function fail to be differentiable? At -1, because if those slopes aren't the same at -1, what happens in the graph? Yeah, it's like a kink, right? So it wouldn't be differentiable at that point. Okay? So you did the same thing with the derivative that you did with the original function, and you plugged -1 into both of them and determined if they were or were not equal to each other. And what did you get there? 9 and 9. So is the function continuous on our interval? Is it differentiable on our interval? Yes, so we write that out. Since f of x is continuous on the closed interval and differentiable on the open interval, mean value theorem applies. First block I wrote apples. Mean value theorem apples. I don't know what kind of apples those are, but there they were. I guess I was, because I just definitely left out the I and wrote apples. Good? All right, now Maggie, now that we know that the conditions are met, the mean value theorem guarantees that what's going to happen on our interval.
The calculus slope equals the average rate of change.
Good, yeah, the instantaneous rate of change or the calculus slope or the derivative is going to be the same as the average rate of change of this function on the interval. So we have the derivative, yes?
Yep.
What do we not have? The average rate of change. Can we find that? I hope we can find that. So we're going to do f of 0 minus f of -2 over 0 minus -2, or backwards as long as you're consistent, right?
Yep.
How do you get f of 0? Plug it in. How do you figure out where you plug 0 in when you're dealing with a piecewise function? The domain restriction tells you. So is 0 less than -1 or greater than -1? Greater, so where did you plug 0 in? To the second one, and when you did that, you got what? -6, yes? Okay? But tell me about -2. Is it smaller than -1 or bigger than -1? Smaller, so you plug that into the top one, and when you did that, you got -18. So you ended up with what? I don't know.
I was like, wait,
That's crazy.
I know, I was like, well, I got that.
Zeros is more than the twos. What did you get at your average rate of change? 6. Good, all right? So we know that somewhere on the interval from -2 to 0, this derivative that we found has to equal 6. Now, when you're dealing with a piecewise function, you have 2 pieces of the derivative, yes? So what do you have to do? Yeah, you have to check them both, right? Because on both of these inequalities, both of these domains, part of our interval is smaller than -1, and part of our interval is greater than -1, right? So we got to check both parts for possible solutions. So we'll set the top part of the derivative equal to 6, and the bottom part of the derivative equal to 6. How do you solve this? Yeah, and you did all that, and you got what? Did you like -5/2? No. Why do you not like -5/2? It's not on the interval. I mean, you may personally like it, but in this problem we don't because it's not on the interval. So we're going to throw it away. Right? Okay. How do you solve this? Before that. Yeah, get it equal to 0. And if you want to take out a 3, you can. Either way, it's not factorable. So you put it in your calculator. There were 2 x-intercepts, but how many of them did you care about? 1. And the 1 value between -2 and 0 was what? -0.732. Very good.
That is not what I got -2.73. Or, I'm sorry. What? What happened?
That was
What? I grabbed it and then
What?
quit. That's very rude.
Excuse me. I apologize.
Oh, okay. I can't do domain. I thought the other one wasn't in the domain for some reason because I'm down. That's fine.
You good now?
Yeah.
Yeah.
No, not really.
Did your graph cross the x-axis at -0.732? And you understand that that's between -2 and 0? And that the one that's positive is not negative, so it can't be between -2 and 0? Okay.
Fun time. I'm just thinking about it.
I mean, at least you did the calculus, right?
I can calculus, I just can't math.
Here we go.
How are the 3? First of all, it's so
Wait, can they like
They can hear you.
Hey!
Hey.
I like wave for no reason.
Marlon's waving at y'all, everyone watching the video. So there's that.
Here is not much. Maybe we should test it. We should say, say some code word. Say the code word is.
Oh, it's parent.
But like later, make sure you watch the whole thing.
Yeah, we'll do it at the very end.
Okay. No, but do it
Not
in
very
the
end, like in the middle, like when we're doing the
In
practice.
the middle of the important part that's actually new that
Yeah,
you don't even
not
watch.
the end, because you get to skip it.
But now they know to skip it.
Oh,
Wait, you're not going to know it's the middle.
Yeah, when's the middle?
Because it's not the middle of the recording, because this isn't the recording.
Oh.
He's not smart enough to figure out the time at the end.
No, really. Well, you might come in and say, "Hey, I didn't like y'all insulting me on that recording," and then we'll
Then we would know.
Yeah. Why is there a tiny screw on your desk? I thought you could say that Chinese.
Is someone lose their screw?
Oh my god, I'm so sorry. I knew this.
I don't even know what that could have possibly come from.
Oh, don't sit down in your chair.
Tyler, did you take this out of the chair when you sat in it? It's like a break on it.
Sit down in the chair.
That will crush it on the steam.
Yesterday, I did not notice it.
The screw? Because he took it out so that would fall down. Alright, so in number 2, it wants to know if Rolle's theorem applies to this function on the interval. So how many conditions do you have to meet for Rolle's theorem to apply? 3. What are they?
Continuity.
Continuity, differentiability, same y values at the endpoint. So sine of x squared, continuous on the interval?
Yes.
Yes. How do we figure out if it's differentiable on the interval? Either you know that that's differentiable or you find the derivative, and at some point we're going to need that derivative anyway, so we might as well just find it now, yes? What rule do you have to use to find the derivative? Chain rule. So the outer function is what? Sine, what's his derivative? Cosine. And that gets multiplied by 2x. Is that defined everywhere? Yeah. Okay. So then the third condition that has to be met for Rolle's theorem to apply, that the y values at the endpoints have to be the same. So we want to know, does f of 0 equal f of the square root of pi? Yes?
Yeah.
Well, how do you get f of 0? You plug 0 in. And here we're going to plug in the square root of pi. And what's the square root of pi squared? Pi. Hold on, Daniel. What's the sine of 0? And the sine of pi. So, yay. Now there's just going to be an awkward.
Yeah. Oops, I have some voltage.
Well, they're better in the first one.
What?
Awesome.
Did you say they're better than first one?
No, it's good. The side houses are better in the first one because there's all the chocolate.
Oh.
You don't even know, Daniel.
Yeah, I'm not- yeah.
You don't even know.
We just had a 5-minute conversation on us.
All right.
I like
And the most random ones aren't even here today, so.
I know. Hey, man, it's good never.
So, since the function is continuous on the closed interval 0 to square root of pi and differentiable
We didn't write for the
over interval, and what else is true? F of 0 equals f the square root of pi, Rolle's theorem, apples.
Oh my gosh.
Both them.
It's been.
So what is the conclusion of Rolle's theorem? If all this is true, then on the interval, what has to happen? There has to be a place where the derivative is 0 because it guarantees us that somewhere on the interval we're going to have a maximum or minimum value. Yes? How do I solve this? Split it apart. When does 2x equal 0? Do we keep 0?
Yes. Or is it no? No. Yeah. I don't know. It's differentiable.
Yeah, right, yeah, you can't, I mean, what we're saying is that somewhere on the interval the derivative equals 0, right? 0 is on your interval, but it's at the endpoint. Can we talk about the derivative at the endpoint? No, so can we use that as one of our answers? No, or as our answer. Okay? All right, now we get to solve a trig equation, which is everyone's favorite thing to do. Okay? So, there's nothing outside of cosine, right? It's all by itself. So what you do is you ignore the fact that this is x squared, and you find the angles on the unit circle where cosine is 0. So where is cosine 0? Pi over 2 and 3 pi over 2. Now technically, we also generate all those coterminal angles, yes? But we're living on an interval, agreed? Okay, so do we think that like 27 pi over 2 is going to fall in our interval? No, probably not, right? Yeah. So we don't care about all those coterminal angles. But this is an x. What was inside the cosine function? X squared, right? So how do you get x? Take the square root. So what do you get? Yeah, you technically get plus or minus this, and plus or minus this, and plus or minus all their coterminal angles, right? But what's the only one that's on your interval? Square root of pi over 2. Well, I would hope so, because you wouldn't even have to work the problem.
So I know it's kind of deep for some people who are living on minimum.
Do I
So it's kind of deep, so they're living on minimum.
living on an interval? I mean, I guess technically we are. Then we're a periodic function. We just start over and do the same thing every day. Except Saturday and Sunday, then throws off.
It's like the one that's like this and it goes like this.
Yeah,
Rhythms.
yeah. I'm actually looking at you like that.
That's what it's actually called.
I know, she was making a really evil face at you.
That's on the peak.
Is that in biology?
Maybe so.
Psych.
So we learned psychology.
That actually was on my AP.
Or did you take some of it?
I don't remember that.
That it probably was.
Ouch. He said, I don't remember that being on the exam. He said, then it probably was.
You always forget everything.
Look, I did write one of the short answers, so come forward. So you can do it, but just not get them. Like
On the Christmas tree in multiple choice section.
I
I want to know like the funny stuff. There's students told me about kids that just wrote all kinds of stuff on this.
No, I keep waiting for them to send us the old, like last year's FRQs. I don't know what they're waiting on. Maybe I'll get Miss Lacoste to call them and ask her why we haven't got them.
Maybe they
Oh,
just
we
forgot
forgot
about
about
us.
that.
We should have them by now. All right, in 3 we have a function defined as kx squared minus natural log of x for all x greater than 0, which is good since that's the domain of natural log. And k is a positive constant. What do you have to do in part A? Find the derivative and the second derivative. This should be pretty like you shouldn't really have to think very much about this. What's the derivative of kx squared? 2kx. And what's the derivative of natural log of x? Or x to the negative, whatever makes you happy. All right. To get the second derivative, we just take the derivative of that. What's the derivative of 2kx? 2k. And what do you get when you take the derivative of 1 over x?
Plus 1 over x squared.
Good, because the negative from the exponent you bring down will make the sign a positive. Then when you subtract 1 from the exponent, it's negative 2. Good? That wasn't too bad, huh? Kind of nice. Didn't have to use any kind of crazy rules. Just nice, simple rules. In B, it says, for what value of k does our function have a critical point at x equals 1? So what happens at a critical point? The derivative is 0 or the derivative is undefined. So that's places where the function might have a maximum or a minimum. Yes? Okay? Yes. No, because for it to be, hold on.
Well, I mean, not in this problem, but if it's where the derivative is undefined or has a maximum, then it could be an endpoint.
But when you talk about critical numbers, you're not usually restricted to an interval. Okay? So, like when we are doing the extreme value theorem, and we know we already have to test those endpoints. So even if they are places where the derivative is 0, we're going to have to test them anyway. So you don't actually have to figure out what the derivative is.
No, laughing at Caitlin. I need to turn on this room staring at Caitlin, and I thought I was just staring at each other. Actually, I was just randomly looking at Caitlin. Yesterday. So I was talking. I'm being the Anna.
I'll apologize. I don't know why they're so weird. I can't explain it.
It's unsettling. They stare at me.
Yeah, you can do it far away.
I'll stare at me.
Yeah, I'm
That's the best part.
So if we want the function to have a critical point at 1, what do we do mathematically? When I count, you just go
Plug in 1 as
set.
x instead of equal.
Plug in 1 for x in the derivative and set it equal to 0. So we're going to. So if we plug 1 in, what do you get here? 2k. And if you plug 1 in here, you get what? 1. Okay? So what is k?
1/2.
1/2. So when k is a half, what does our derivative look like? Okay, if you replace the k with a half, what's your derivative going to be? X minus 1 over x, right? Because the 2 and the 1/2 would cancel each other out, which is nice. Because in the next part of the problem, it wants us to determine if that critical point we just forced to happen at 1, if it creates a minimum on the function, a maximum on the function, or neither on the function. So how do we determine if our critical point is a minimum, a maximum, or neither? Yes, right? Test the intervals on the number line, see what's happening to the left of 1, to the right of 1, and then make a decision from there. Okay? So, let's see. What's the number between 0 and 1? A half. What's 1 divided by a half? 2. And a half minus 2 is going to give you what kind of number? Negative. So if the derivative is negative, what's happening to the function? It's decreasing. Okay? What's your favorite positive integer larger than 1? 7. So that's better than the 73 and the 47 we used at the second one. So if you plug in 7, that would be 7 minus a 7th. Positive or negative? Positive. So what's happening over here? Well, over here we're increasing. Okay? So at x equals 1, f of x has a minimum. How did you know?
Because the derivative is changing.
Look at that you go. Because f prime changes from negative to positive. Awesome. Remember, you can never use the function to justify behavior on the function. That's like saying the answer is 2 because it's 2. Okay, right? It's obviously a minimum because it goes from decreasing to increasing. So you got to talk about how we know that the function goes from decreasing to increasing. Okay? Good? People will write, it goes from decreasing to increasing. And that gets you nothing. I think we've read this enough times that y'all can do it in your sleep. All right, let's talk about linear approximations. Woo! Few notes. Good news though, the math in this you know how to do already. It's just an application. So it should not be bad. Probably want an apple. I don't even have enough. I have a pineapple. Probably have something to do with
Tasty. It looks like a pine.
There must be some kind of like to do.
It's not a dumb fish.
And then it looks like a pineapple.
What was wrong? From the buffalo. What's your sickness?
I have fruit salad every day.
No, yeah, I know. That's probably I probably use gloves. Shut up. Yeah, John, no, I know.
My friend Rachel ran for 30 years.
I was thinking a logical, wrong direction.
I would have
Yay!
Oh.
Yay! Look at you go. What was your score? Holy cow, Macy got console.
Wait, what did you say?
Show from a 25 to a 29. That's awesome.
You need to take it again, buddy.
I feel like I should have taken it.
That's awesome. Wow.
One whole plate.
I didn't want to look. I thought I did horrible. Yeah, the science portion was awesome last night. And I was like, science is going to be stay in the 30s. I'm going to pray for us.
I'm gonna take this next one.
That's what I did this time.
That'd be a good job. 32.
I was just like, it's the same scholarship from 32 to 30. Yeah, I mean, now I know.
Where?
This one,
There you go.
But it's probably more likely. It's probably more likely that you'll get awarded the scholarship.
And
than
then
that
I'll do
higher.
extra stuff too, like in Pemmy to 32 and
You did a
36.
better scholarship. Yeah, that's
You get like the limousine.
yeah, it's in this
I mean, it's not what it's called, but like it's not,
That's when you get a free card from Nick Saban's.
you get a handshake and a car. They say
Made it 26 fourth time in a row.
For the what?
Fourth time in a row.
Nice.
that's fun.
If only you were playing the slides. Guys.
I would take it again, but I basically can't take it again, so.
You have extremely high reliability.
Yeah. I dropped last night.
I know, I think I
Because
was
I
You can't speak
something-
on the validity.
There was something else I wanted to do that weekend.
should have.
Yeah, that wouldn't change
In
anything.
retrospect.
Maybe like it's not even matter after us. I mean, after college.
Like college matters.
Yeah.
Yeah.
Well, I guess it depends.
I'm hoping the extra $1,000 a year I could have gotten if I just had 30 would balance out with the fact I'll go to business. Maybe that'll balance out my class.
Yeah,
Like,
maybe.
Maybe, hopefully. If not, then I did all.
You actually should come out on the. How many credit hours do you have right now?
So if I pass calculus, yes, I'll have 38.
And you counted calculus as 4, yes. But it's usually 4. Cal 1 and Cal 2 are 4-hour classes.
I want to do that.
38. So, yeah, that's way more than $3,000. But I guess it's $3,000 a year, so that's $12,000 over 4 years. That's a lot of math. Yeah.
For me, if my school down there made it where overall college is free funding for USA.
Woohoo! That's exciting.
I just have to pay the first semester and then get reimbursed.
That's exciting. But you're going to take it again, yeah? Well, you have to.
So I don't have to pay for first semester, and so I get more money at the end of college.
Where are you going? Isn't it like March 20th, y'all?
Yeah, your one. I don't do well this month for college. Let's see.
Hey, you're so dramatic. Okay. All right. So when we talk about linear approximations today, it's going to be an application of the tangent line. Okay. So do you all know how to write the equation of a tangent line? Hopefully. What are the things that you need to write the equation of a tangent line? A slope and a point, yes? Okay. So you'll typically be given the x coordinate of that point, plug it into the function to get the y coordinate. How do you get the slope of the tangent line? Find the derivative, yeah, and then plug the x coordinate into that, okay? So when we deal with linear approximations, mathematically what you're going to be doing, calculus-wise, is the same as writing the equation of a tangent line. Okay, it's just now we're going to talk about using that tangent line to approximate values on the original function. Okay, so for instance, and this is going to be where this recording thing is annoying because I have to keep doing this, so I can't write on the whiteboard. So, I better watch it. Because I can't write on the whiteboard because I can't see it.
Well, they can suck it up.
Say you have this function. Yes? Okay? And you want to know f of 3. Anybody in here on the top of their head know what the sine of 3 is? Daniel, don't raise your hand. It's not fair, you already did this. You have an unfair advantage.
Well, I have calculators.
Without the use of your calculator, anyone in here not named Daniel know what the sine of 3 is off the top of their head?
0.14.
Without your calculator, you fools. You do not, correct? Why can you not? Okay, here we go. Should exclude you as well. You people always come in, but it's not class period. I can't get rid of you, and this is what happens. Especially Jason. I don't even teach him anymore. He just wanders in.
Three is not on you.
Thank you. 3 is that. You got a finger you can throw. Okay, all stressed out. A finger you can fold in that represents an angle of 3?
No.
No, right? So you cannot evaluate the sine of 3 without me using your calculator, okay? So what we want to be able to do is we want to be able to evaluate things. And it's not really even going to be evaluate, but approximate the value of things like the sine of 3 if we don't have a calculator there, if we can't just put it in the calculator, like on the no calculator part of your AP exam. So the way that we're going to do this is we're going to use the tangent line to help us. Okay, so we're going to come back to this example, but I don't want to do it yet because I don't want to have to graph the sine of x. So we're going to use something kind of easy. We're going to talk about x squared. So write that function down.
You haven't even written any notes about it yet.
I know. Weird. You'll have notes. They'll be there.
I tried the other equation.
Because we're going to come back to that one. That one just makes it's a good example because you can't find that on your own, right? Because technically what we're about to do, you could do by hand. You just probably don't really want to, right? What if you wanted to find f of 1.03? Yeah, if you have a calculator, you just do 1.03 squared, right? Do you really want to have to multiply out 1.03 times 1.03? No, okay? So, think about what the graph of x squared looks like. We should know that. What does the graph of x squared look like? A parabola. Why y'all say that so awkwardly? Like you didn't trust yourself.
I never trust myself. With any answer. I think, yeah. That's a pretty nice one.
Thank you.
More.
I was a little worried because drawing it on the air is harder than drawing it on the whiteboard, but that's pretty good. So there's your parabola, yes? Okay. So, do you know what f of 1 is? Yeah, you can square 1 pretty easily in your head, right? Okay. So could you write the equation for the tangent line to this curve at 1? Yeah, that's a really bad line. Just go with it, okay? All right, you could. At 1.03, which is just like right, very, very slightly to the right of 1, right? Is the point on the tangent line pretty darn close to the point on the graph? Yeah. So if I could figure out what the equation of this tangent line is, which we know how to do, and I plugged 1.03 into that linear function, wouldn't that be pretty close to the value of this function at 1.03? A decent approximation? That's what linear approximation is, okay? What it does is it basically takes the function and it linearizes it, okay? It creates a linearization, and it does it using the tangent line. Because really close to this point of tangency, the tangent line and the curve are almost identical. Yes? Okay? Now, would I want to use this tangent line to approximate f of 7.5? Why? 7.5 is way over here. Is this line still going to be really, really close to this curve all the way over here at 7.5? No, not even close at all, right? Because the line's going to go this way, and the curve's going to go that way, and they're going to get further and further and further apart, right? But near that point of tangency, aren't the line and the curve almost the same? Yeah, and we know that because we know that things that are differentiable exhibit that local linearity that we talked about at the beginning of the semester, okay? And we know that near that point of tangency, if we zoom in far enough, the curve starts to look like a line, right? And not just any line, it starts to look like a tangent line there. So near that point of tangency, the curve and the tangent line have the same y values, okay? So what linear approximations are going to allow us to do is going to allow us to evaluate functions or approximate the value of functions using the tangent line, which is sometimes a lot easier to plug in. I mean, think about if you had this function. You want to plug numbers into that? No. So could you pretty easily find the tangent line to that curve at 0? Yeah, right? You know the derivative of that? Pretty quick. Plugging in 0 is not real bad. So it wouldn't be a lot easier to plug numbers into the tangent line rather than to plug numbers into that? I think so, right? So that's kind of how this is going to help us out. Okay? So you know how to write the equation of a tangent line. This is just big kid notation. But all it is point slope form. Okay? This is just y minus y1 equals m times x minus x1 in grown-up notation. You're big kids now. So we're going to use grown-up notation, not algebra 1 notation. Okay? So we have this function f of x, and the equation of the tangent line is f of x, it just means y, right? Minus f of a, which is the y coordinate of the point, equals f prime of a, which is the slope, right? Because that's the derivative at the point, times x minus a. Grown-up notation, okay? Now, here's the only difference from a normal tangent line to a linear approximation. When we use our linear approximations, we're using them to approximate y values on the function. So we want our linear approximation to read y equals, not y minus stuff equals stuff, okay? So anytime you write a linear approximation, you're going to put it in slope-intercept form, okay? You're going to get that y by itself. Another thing you have to be careful about is if the function is called f of x or the function is called g of x, you want to use that same notation in your linear approximation because it's directly related to that function, right? So we're saying the values of that function are approximately equal to the values on the tangent line. Okay, and the cute little squiggly sign means approximately. So when you write the linear approximation, you're always going to use that approximation. Okay. Well, whatever it is, whether it's f, but whatever the function is called, you want to use that same name for your linear approximation. I missed that. It was going right in my nose, I feel like. But I caught it. Alright, so what this linear approximation will do is it creates a good approximation for values of the function near that point of tangency. So rather than having to plug the numbers into a complicated function, we can plug the numbers into that linear equation and that's a whole heck of a lot easier. Alright, so we'll pick up from there when the lunchtime is over. You can keep writing, I'm just going to pause this.
Not really.
Hey.
Earlier we were talking about the function f of x equals the sine of x, and we wanted to be able to evaluate this function at 3, but we decided that we cannot do that without our calculator. So what we're going to do is we're going to use the linearization of this function. At some x value that we know how to find the sine of to approximate f of 3. Okay? So what? So pi, right? Because when you're dealing with a trig function, you want to use one of the special angles that's on your unit circle, and hopefully we all know the decimal approximation of pi is pretty darn close to 3, yes? So if we want to figure out f of 3, if I can write the equation of the tangent line to this curve at pi, then I can use that tangent line to help me evaluate f of 3. Okay? So when it says use the linearization or find the linear approximation of, and that just means write the equation of the tangent line. Okay? So what do we need to write the equation of the tangent line? A point and a slope. So what do we know about our point? It's going to be pi as the x-coordinate. How do we get the y-coordinate?
Plug it in.
Plug it in. What's the sine of pi? 0. How are we going to get the slope? The derivative. So what is the derivative of sine? Cosine. And what is the cosine of pi?
Banana.
-1.
What I said.
Okay. So now can we write the equation of our tangent line? Alright, what's the equation of our tangent line? Start in point slope form for me.
Y minus 0
Y minus 0
equals
times. Okay? So this is the equation of the tangent line. Okay? So when we deal with these linear approximations, we got to do a couple of things. We got to put this in slope-intercept form, and we don't want to use y because our function wasn't named y. What was our function name? F of x. Okay? So we're going to say f of x is approximately, right, because the tangent line and the curve are not the same. They're just close to each other. Our y values are approximately equal to, what do you get when you distribute the -1?
negative x plus pi.
Negative x plus pi. So there's our linearization. Okay? So as long as we're pretty close to pi, we would get the same value out of this as we would get out of the original function, or close enough to it to call it the same. Okay? So we want to evaluate this function where? At 3. So we're going to plug 3 in for x in our linearization. And we should be able to do this, yes? What is -3 plus pi?
0.14 minus pi. Something.
Yeah. 2, 6, something.
Okay, wait. You're right. Okay. She doesn't love pi. She does.
So why don't you take out your calculator and tell me what the sine of 3 actually is.
6.141.
Pretty darn close? Yeah, right? So without this linearization process, you have no idea how to evaluate the sine of 3 without your calculator. But you can easily write the equation of the tangent line near 3 and figure out an approximation of the value.
We got a calculator on the AP exam. You can use the one.
Yeah. Yep. Or a linear approximation or something that sounds like that. Yep. Good? All right. Were you here for that part of the conversation?
We didn't have to talk about
I was like, were you here before she left? After she left. Alright, in this first problem on the front, there are 4 functions, okay? And what it wants you to do is it wants you to find the linearization of each function at 1, which means write the equation of the tangent line at 1, okay? So instead of us doing this 4 times, I'm going to break you into 4 groups, and I'm going to give some of you f of x, some of you g of x, some of you h of x, some of you j of x, okay? And you're going to write the linearization for your function, and then we'll put them all on the board together, and this works out to be really interesting, so we'll talk about them, okay? So how many of you people are there? 20-ish? So let's go groups of 5. So let's see. Yeah, y'all get j of x. Congratulations.
why do we do that way?
Because that's how I've been going all day, honestly. All right, you 2, and then the front 3 people on this row, you do h of x, and then you 2 and the next 3 do g of x, and then the rest of you do f of x. Yeah. You can talk about it together. Okay, or not, whatever. For those of you watching this video, you can find these examples on the website under linear approximation. approximation.
Under a big banana. Oh my gosh. Should I consider yet?
Best translation. Just makes it different. That's cool.
Two. Two. Well, yes.
There you go.
What have you wrote?
Yes. I don't know. Very plug it in exactly. We plug one into two.
Yeah. To get the slope of this point. Wait, plug it into what?
Into your.
No,
Okay.
just find me the equation.
Oh. Okay.
Because at the point, right, at that point of tangency, the function and the line are exactly the same. So whatever the y-coordinate of your point is what you would get if you took x and plugged it into the line too, because they intersect there, right? So it's only really useful to us away from that, a little bit away from that point, because if x is 1, you can plug 1 into anything, you know? But if x is 1.1, I don't think anybody can plug 1.1 into those functions and know exactly what you're going to get necessarily, right? So it helps more when you are moving a little bit away from that x. All right, in f of x, what did you get as your point? People over there. 1, 0. What did you get as your slope? 1. So what was your linearization? F of x is approximately x minus 1, right? Yeah?
Yeah.
Okay. All right, in g of x, what did you get as your point? 1, 0. What was your slope? 1. What was your linearization? X minus 1. How about that?
I hope they're all the same.
What do you not know how to do? What do you not know how to do? What do you not know how to do?
Okay, so I have the derivative now.
Which is cosine of pi over 2 times x minus 1, right? Yeah, so you want the derivative at 1, so you plug 1 in for x.
So cosine 0 is 1. It's just 1. Okay.
Okay. All right, so for h of x, what did y'all get as your point? 1, 0. What did you get as your slope? 1. What was your linearization? J of x, what did you get as your point?
Same thing.
Same thing. All right, so this is kind of interesting, okay? Because tell me what the graph of an exponential function looks like. Like, what would the graph of f of x look like? Like this, right? Yep, okay. What about x to the 4th minus 3x plus 2? What is that?
Big graph.
Or a polynomial. We don't really know what that x is going to do to us, but some kind of polynomial looking thing, yeah? What about natural log of x? It goes like this, right? What about sine? Right? Do any of those look the same? No. But at 1, do they look the same? Yes, they go through the same point and they have the same slope. That's kind of crazy. Okay? So what we're going to do is in part 2 on this question. It wants you to use the linearization to estimate the value of the function at 1.1. Now let's think about this. If all 4 functions have the same linearization, what's going to happen when we plug 1.1 into the same linearization 4 times? We're going to get the same thing, right? So if we want to approximate f of 1.1, we would plug 1.1 into here, because we really don't know how to plug it into here, right, without our calculator. What's 1.1 minus 1? If we want g of 1.1 using our approximation, what are we going to get? 0.1. If we want h of 1.1 using our approximation, what are we going to get? 0.1. Same thing for j, yes? Now, do we really think that these functions have the same y value at 1.1? No, because we're moving away from that point that they all share, and we know that they don't look the same, right? So here's what I want you to do. Whatever your original function was, take your calculator and actually evaluate it at 1.1. What we want to know is how good these estimates are. Because what we want to determine is what makes our estimates, how can we get a better estimate, what kind of functions produce better estimates than others. Kelly knows, because he was here. All right, what is f of 1.1 exactly? I mean, well, as exactly as you can get.
0.105.
Yeah, that's good. I'm happy with that. Pretty close, yeah? Not bad. Agreed? What's g of 1.1? 0.1641? Is that as good as this? Not even close, right? I mean, you're like 0.05 off here. That's not great, right? What's h of 1.1? 0.095? Decent? Yeah? And what's j of 1.1?
0.099.
So, which approximation gave us the best estimate of the value? J, okay? So, j of x gives the best estimate, or the best approximation. And who gives the worst? G of x. All right, so now we got to talk about y, okay? So look at f of x and g of x, all right? We estimated that the value was going to be 0.1, right? Tell me about the actual values here. Are they larger or smaller than what we estimated? Larger, so we underestimated the value, right? So what we estimated was smaller than the actual value. Yes? Okay. What about over here? We overestimated because what we thought based on our tangent line was bigger than what the actual value is. Yes? So we got to figure out what mathematically is making our approximation an underestimate versus what's making it an overestimate. Okay? So I want you to think back to that parabola we drew earlier. Probably fine. Maybe not. I guess I can't find it, so we'll just draw it again. It's not a great parabola. We're going to pretend that's the x-axis. We drew the tangent line at 1, right? Okay. Do you think if I use the linear approximation here for like 1.03, would that value be bigger or smaller than the actual value?
Smaller.
Smaller. Why? Because the tangent line's beneath the curve, yes? Okay? Why is the tangent line beneath the curve? It's concave up. There it is, right there, okay? So if the function is concave up, the linear approximation is an underestimate because the tangent line has smaller y values than the actual function, right? Yeah, linear LA. I just don't feel like writing out approximation for the 4 billionth time. Okay. So, and we know that if f of x is concave up, that means the second derivative is greater than 0, right? That's how we determine concavity. So if you flip the parabola upside down, and you draw the tangent line, now where's the tangent line with respect to the curve? Above, so our approximation would be what? An overestimate. And we know that that happens when the second derivative is less than 0. Okay. So we know from that, in the 4 problems we just did, that 2 of them were concave up near 1 and 2 of them were concave down near 1, right? So what do you think made g of x so bad? Probably the big banana, yeah. So it actually does have to do with the word big. Because the further away your second derivative is from 0, right? What does the second derivative tell us besides concavity? The rate of increase or decrease. So if your second derivative has a large magnitude, your function's changing really quickly, right? So the curve is getting further away from the tangent line faster, okay? All right, y'all hold on to that. We'll probably do some more with that tomorrow as like your recorder. I'm going to give you, if you weren't here yesterday, here's the study guide for your test. And then this is 5 problems where you're going to write the linearization and then use it to estimate. And this is not optional because it's a new concept. Okay? Take one and pass it by. That's super common. Tomorrow. But it should take you literally like 15 minutes at this.
Oh, yeah.
I do not.
I need to check my blood.
Finish your banana.
No, I did not.
That's because they need.
Remember, tomorrow we'll go over your online assignment, so bring it.
Oh, there's the banana.